Hello everyone, and welcome to the second edition of the NGRES, Next Generation Real-Time Embedded Systems workshop. I am Federico Terraneo, the program chair of this workshop, and thank you everyone for attending. We will spend the first minutes waiting for the attendees to join, and then we will start with the first presentation. Okay. The first paper that is going to be presented in our program is an invited paper. It's called A Comparative Evaluation of Latency-Aware Energy Optimization Approaches in Many Core Systems. And the presenter will be Khalil Esper, which is already connected. As we have already anticipated, and as you may already know, the program of the workshop has already been published on the NGRES website. So you can already start downloading the papers if you want to have a look at them. And also, if you have some questions, since you can already read the paper, if you have some questions during this time, you can ask them during the workshop itself. Okay. I think that we should wait just a little bit more for some attendees to join. I mean, I have started. Yes, it is started. I see the pause and stop recording buttons, so it is started. Oh yeah, this is why. I see the attendees, which are just in a different tab compared to the panelists. So we have already 16 attendees. So now it makes much more sense, okay? Because I was watching at the panelists and the number didn't grow. Okay. So given that the attendees have already joined, I think we can start with the presentation. Khalil Esper is a PhD at Friedrich Alexander University, right? Okay, you can introduce yourself and start with the presentation.
Should I introduce myself or?
Yeah, here you are.
Yeah, so my name is Khalil Esper. I am a PhD student at University of Friedrich Alexander University at Erlangen, Nuremberg, and I am doing my research in optimization in multi-core systems. And I am part of the InBasic project, which is run in the between three universities of FAU and Munich and Karlsruhe. Yeah.
Okay, you can share the screen and start your presentation.
Welcome everybody, and thank you for attending our presentation of the paper, A Comparative Evaluation of Latency-Aware Energy Optimization Approaches in Many Core Systems, written by me, Khalil Esper, and Dr. Stefan Wildermann and Professor Jürgen Teich of the University Friedrich Alexander Universität Erlangen-Nuremberg, FAU, Germany. The outline of this presentation is as follows. In the introduction, I will talk about the enforcement problem and how we can enforce non-functional program properties on the many-core system, and specifically how we can save energy while satisfying latency goal. And this has two types of solutions. The first is application-specific, and the second is feedback-based. In the feedback-based, we have two techniques. I will talk about the control theoretical technique and the new suggested finite state machine-based technique. After that, I will present the results of the comparative evaluation, and finally, a conclusion of this work is given. In the introduction, I will talk about the system model and the problem that we are trying to address. The system model consists first of many core architecture that typically has memories and I/O units and cores connected via network on chip routers. Second, the application, which is typically realized via actor graphs that consist of many actors communicating via tokens. Applications, and especially streaming applications, have variation in the execution latency due to the changes in the workload and environment, and such applications have non-functional properties that need to be respected, such as the latency goal requirement. Third, the requirements, which could be, as we just said, the latency goal, or the energy consumption, or even temperature thresholds. Finally, the enforcement, which is done using the available configurations in the system, and this could be, for example, the number of cores and the power mode, which is the voltage frequency setting. Now, the problem that we address is that when we run the application on the many-core platform, we want at the same time to enforce the set of requirements of the executed applications. And this is done by choosing a suitable configuration such as these requirements are satisfied. Specifically, we want to choose a configuration to be applied in the next control period such that the energy is minimized while satisfying the latency goal. And in the literature, we have two types of approaches for this. The first is application specific, and the second is feedback based, which contain the controls theoretical approach and the new suggested finite state machine approaches. We will start with the application specific approach, which specifies for each specific workload the configuration that achieves the latency goal while minimizing the energy consumption. However, it has a disadvantage that it lacks the ability to adapt to unseen workloads or applications. The application-specific approach starts with first the profiling phase, which aims to form and parameterize a latency and an energy model for a given application or a task. So it depends on one or more workload indicators. In our case, would be the number of features in each image frame and the configuration. So it starts by determining the execution latency per image for a representative set of input images in using simulation. And after that, the latency for processing one feature on one core in the highest voltage and frequency mode is determined for each image by dividing the found latency previously by the number of features I in that image. The next step is to determine the Pareto front. After determining the latency per feature, a model for estimating the latency for processing I features in an image when employing the number of cores and the power mode is derived or learned. It's done by conducting a design space exploration based on a given latency deadline. And the goal is to determine the required configurations that enables to process the workload I within the deadline while consuming the least amount of energy. As shown here in the figure, we see the Pareto front optimal configurations that achieves the minimal energy consumption shown in the y-axis, and for each enforceable workload that's shown on the x-axis. Finally, the optimal configurations from the previous step are stored in a structure and queried online before each execution to find the configurations that will be energy minimal and achieves the latency goal, and then it will be activated as an action. Now we have the feedback-based approaches. The advantage here, there is no need to know the expected workloads before the start of the execution. It only needs the feedback of the previous execution. So it computes the next configuration based on the feedback error, which is the difference between the latency goal and the latency feedback it got. It has two approaches, first using control theory, and the second using the suggested FSM-based enforcement. Control theoretical approaches use the control signal concept from control theory here as an abstraction for latency. So they use a model of the relation between the execution latency at iteration t and the previous control signal. They also need to compute the base signal, which is a time-varying parameter that represents the execution latency of the currently expected workload using the lowest possible configurations in the system. As we can see in the figure that the controller uses the feedback error, which is the difference between the latency of the previous execution and the latency goal. It uses this feedback error to compute a control signal, which would also depends on the previous control signal and the other control related parameters. And it will be later used by the optimizer to find the optimal configuration to be applied. Next, the optimizer takes the computed control signal and transforms it to optimal configurations to be applied in the next control period. It uses an algorithm to search a structure called the configuration map, which contains the available configurations in the systems along with their speed ups. It computes the schedule of two configurations that most close to the control signal and also have the minimal energy consumption. Another possible feedback-based approach could be done using finite state machine, and hence our suggested approach that neither needs an offline stage nor the introduction of control signals. Finite state machines have a strong mathematical formalism, so the requirements of the program properties could be formally proved to hold in all states and for all inputs using proof techniques like model checking. Also, the finite state machines don't need to make assumption on the linearity of the used models or the speed ups. Also, the transitions between the states of the FSM could not only contain one event, like the feedback error, also could contain multiple events and possibly containing other environmental conditions such as temperature. The suggested finite state machine based approach transitions to the same or adjacent states once per iteration t, based on the sign of the error signal. So as shown here in the figure, the FSM controller takes the feedback error, which is computed based on the previous latency, execution latency, and checks its sign. So if it's positive, then we have an error, and we need to increase the speed of the execution by going to higher configuration states. However, it will also consumes more energy. And the same if it's if the sign is if the feedback error is negative, then we could go backward to lower configuration state to save energy. Now we will discuss the comparative evaluation part of our paper. Our case study consists of an object detection application named SIFT, which is a feature extraction algorithm used in computer vision to detect and describe features in images. The different steps of this algorithm correspond to the different actors of the actor graph shown here in the figure, which will be executed on the minicore platform. And during an offline characterization phase, the SIFT description actor, which is used to extract features from images, provided the highest contribution to the overall processing latency per frame. and also had the highest degree of input-dependent execution time variation. That's why we chose him as a candidate for to apply the different enforcement techniques. And the safe description actor has the requirement of execution latency of 80 milliseconds. And we see here in the figure that the controller chooses the number of cores and the power mode to be applied in the next control period, so that the safe description actor achieves this requirement and has a minimal energy consumption. And for the evaluation, we used the InvadeSim, which is a performance simulator for heterogeneous mini-core architectures. So for the controller, we will evaluate 4 types of techniques. First, the race to idle, which will be executing always in the highest configuration level. Second, the application-specific approach. Third, the control theoretical approach. And finally, the suggested FSM-based approach. And for the input, we have 3 types of input for the evaluation. A 5-minute YouTube video from National Geographic, a 14 minutes video of front camera in a car driving through city roads, and finally a sequence of 1750 images with random contents. And shown in the figures are the distribution of number of features for each frame. Now the results. We did the experiments using 2 types of configurations. The first type using 80 configurations where the number of cores were between 1 and 4 and the power mode was between 1 and 20. We see on the left the percentage of deadline misses for each approach, and also each bar corresponds to specific input type. We can see clearly that the race to idle and application-specific approach hardly miss any deadline, because first the race to idle executes in the highest possible configuration, and the application-specific approach executes in the required configuration for meeting the deadline. And then comes the control theoretical part, and finally the FSM, which is slightly worse than the control theoretical part approach, because due to its simple structure. On the right, we can see the energy consumption of each approach, and we see clearly that race to idle executes consumes the highest amount of average energy consumption, because it executes in the highest maximum configuration. And then comes the FSM and slightly better control theoretical approach, and finally the application-specific approach, which has the lowest average energy consumption due to because it executes the Pareto optimal configurations. For the next type of experiments, we fixed the number of cores to 4, so now we have 20 configurations instead of 80. And we can see that the deadline misses now got worse because of the limited number of configurations. However, for the FSM, it got better because now each step has more effect, so it converges faster to the required state of execution. For the energy consumption, we can see clearly that all approaches now suffer from the limited number of configurations and now has more energy consumption, and that's because some of the optimal configurations now are not available. Now, to conclude our work, we have evaluated and compared different approaches for latency-aware energy optimization. First, the application-specific approach, that we have seen that it respects the latency goal whenever possible while consuming the lowest amount of energy consumptions between the other approaches. Second, the 2 feedback-based approaches that include the control theoretical technique and the new suggested technique based on the finite state machines. Both approaches can achieve energy savings that are comparable to the application-specific approach. However, they miss more deadlines. In the end, we believe that finite state machine-based approaches could be an alternative to the control theoretical approaches because they have strong mathematical formality and proof qualities that they could benefit from the different proof techniques like model checking. In addition, the finite state machine-based approaches don't need to make assumptions on the linearity of the plant nor the control behaviors. Last but not least, this work is part of the invasive computing project that is funded by the German research foundation Transegio 89 that consists of a collaboration between 3 universities in Germany, namely Friedrich Alexander Universität Erlangen-Nürnberg, Karlsruhe Institute for Technology, and Technische Universität München. And the aim of this project is to investigate novel methods for the design and resource-aware programming of future parallel computing systems. And one of its goals is the runtime requirement enforcement that enables achieving satisfying the non-functional program properties such as latency goal and saving energy on many core platforms. And finally, thank you for your attention, and I am happy to answer any question.
Okay. So you can stop sharing now. First of all, can you still hear me? Just to
yeah, I'm here.
Okay. Okay, that's perfect. Yeah. Now, I will repeat it every time because it's important that attendees may join or leave. If you want to ask questions at the end of the presentation, you can either do so by voice or using the chat. Since this workshop is recorded and then it will be uploaded on YouTube. As part of the IPIC policy. If you have concern about your privacy, just use the chat. Okay. So let me see. We have. Okay, no, we don't have yet questions in the chat. Are there any questions from the attendees? I think you should do something like ask to raise the hand, and then I will allow you to talk. We are early on our program, so there is definitely time for questions. Let's wait a little bit to see if some question arrives. In the meantime, I think that I have a question about this work. In general, if you consider an approach based on control theory, the design is done in continuous time, okay? So the control law can be seen as an infinite state machine. But as soon as you implement it on a real processor, what happens is that you have to use numbers, a number representation in a computer, which has a finite number of values, okay? And that's true if you use floating point. It is even more true if you use a fixed point representation for performance. So you can see this as a sort of a state machine. Okay, have you considered like exploiting this viewpoint on control theory to like take a control law and simplifying them, removing states that may not be needed in order to achieve a finite state machine?
So actually, the control theoretical approach considers the system to be discrete, not continuous. So, but no, I didn't consider to be continuous.
Yeah. One thing is discretization. Sorry, maybe I did I was imprecise. One thing is discretization, and one thing is quantization. Okay, because discretization is in time and quantization is in the values, basically. As soon as you implement it using floating point, like a floating point is 32 bits, so there's no more than 2 to 32 possible states that a floating point can have. So the state is actually finite when implemented in a computer. But okay, you haven't considered, so that's the question.
Yeah.
We have this is. We have some people who are asking how to access the proceedings. Okay, so that's also another interesting question. I have written in the chat the link. Okay, I don't think it makes much sense to to say a link. So I will just write it so that you can copy and paste it into your browser. This is just the NGRS website. From there, you can get to the program, and there are links to the full proceedings and to every paper that you can download. Okay, so I see that in the meantime, no more questions have queued up. So I think that we can switch to the next paper in our program, essentially. Oh, no, wait, we have another question. Let me, okay, no, it's just, okay. That's fine. So the next paper is EDF scheduling and minimal overlap path routing for real-time time-slot channel hopping network. The presenter will be Miguel Gaitan. Here you are. Okay. I see that you are a PhD student at the University of Porto, right?
Exactly.
So you can. I have a look at your at your bio or something, and it looks like you're also assistant professor at Andreas Bello University in Chile, right?
Yeah. Yes. I hold a position in Chile. Yeah. I was a master's student.
You can present yourself.
Yeah.
Yeah. You can present yourself and then start the presentation.
Okay, so I am Miguel Gutierrez Gaitan. I am a PhD student at the Faculty of Engineering on the University of Porto. I work under the supervision of Professor Luis Almeida at the University of Porto. And I am also part of SISTER, which is the research center in real-time and embedded computing system at the Polytechnic Institute of Porto. I'm going to present a work in one of the line I am working, which is real-time communication for wireless networks. And more information is in the video, which I would prefer to play.
Okay, you can share the screen and start the presentation.
Okay, thank you. Okay. Hello, everyone. My name is Miguel Gutierrez Gaitan. I am a PhD student at the Electrical and Computer Engineering Department of the Faculty of Engineering of the University of Porto. And I'm going to present the paper EDF Scheduling and Minimal Overlap Shortest Path Routing for Real-Time TSCH Networks. This work is a collaboration with Professor Luis Almeida from the University of Porto and Pedro Santos and Meumeu Yomsi from SISTER, the Research Center in Real-Time and Embedded Computing Systems at the Polytechnic Institute of Porto. We frame our work within the emerging context of Industry 4.0 and the Industrial Internet of Things, which, among other concepts, cover the use of wireless technologies in industrial domains, including industries such as oil and gas, automotive, offshore marine, and manufacturing. Within this context, we target particularly wireless standards based on time-synchronized channel hopping, alias TSCH, which is a quite common technology in the industrial realm. In effect, wireless standards such as wireless HART or ISA 111A are nowadays especially popular in wireless sensor actuator networks used to support real-time monitoring and process control applications. Other low data rate but time-sensitive domains, such as audio streaming, can also leverage on this technology, for example, for the purpose of safety audio announcements, or for communication with field personnel within the industrial facilities. Motivated by those related scenarios, but without loss of the generality, we consider for this work the case of industrial wireless sensor actuator networks presenting salient features of typical TSCH-based networks, namely a multi-channel time division multiple access, or TDMA, medium access control, single packet transmissions performed in per slot, per hop, and per channel fashion, centralized routing and scheduling management, and global view of the mesh wireless network topology. We model the network as an undirected graph, G equals VE, where V represents the set of vertices or nodes including the gateway, and E, the set of edges or links between those nodes. As for the flows, we assume time-sensitive network flows with packets enforced by constrained or implicit deadlines, thus targeting time-critical operations. We also assume that at each node, the single packet transmission follows an earliest deadline first, EDF, scheduling policy, thus enables straightforward analysis of the network schedulability. Under this setting, we are interested in the so-called real-time wireless routing problem for concurrent network flows as scheduled under EDF. Here, we look at enhancing and/or guarantee the real-time properties of the network based on routing decisions. We know that similar work in the literature has addressed this problem, but for a fixed priority scheduler. Therefore, to the best of our knowledge, our work is the first to address the problem of real-time wireless routing in TSCH networks under EDF. In order to assess the real-time performance of the network, we take advantage of our prior work on schedulability analysis for wireless industrial networks. In specific, we leverage on the so-called FFDBF analysis when applied to the context of wireless sensor actuator networks, which takes into account the relationship between the supply bound function and the force forward demand bound function. Here, the supply bound function is defined as the minimal transmission capacity offered by a multi-hop, multi-channel network with M available radio channels, and the force forward demand bound function represents the upper bound on the maximum network demand for a given set of network flows. We highlight the importance of this analysis since able to split the upper bound on network demand on two components. One, the channel contention, equivalent to the core contention on multi-core platforms, thus considering the case when all the available channels are busy by high priority transmission, and thus low priority transmission get delayed. And two, the transmission conflicts, an abstraction specific to wireless scheduling, modeling the limitation of the half duplex transceivers to allocate concurrent transmission reception operations on the same node, despite the availability of channel resources. In this work, we focus on the transmission conflicts component, and particularly on its relationship with the concept of path overlaps, which we consider a key factor to improve schedulability. In essence, transmission conflicts can only occur if there is a node overlap between the routing paths of two network flows. To make it more clear, this is the same to say that a transmission conflict between two flows can occur only if both flows share the same node within the routing path. While such a situation does not necessarily imply the existence of a transmission conflict, it has an impact on the worst case end-to-end network performance. Based on such an insight, we aim to find a set of route paths which minimize the overall number of node overlaps in the network, while improving schedulability. To this purpose, we propose to use a greedy, rather effective heuristic that minimizes overall path overlaps, leveraging on a weighted shortest path routing algorithm. The method can be divided into three major steps. One, the initial solution. Two, the greedy search, and 3, the best solution. And the first step, the method provides the initial solution. This is a set of road paths based on the classical Dijkstra, therefore only based on a hop count shortest path criterion. Then the overall number of node overlaps is computed, and a weighted graph with links weights based on the individual degree of node overlaps between the roads is obtained. This new graph is used as an input for the next step, which is the greedy search. The greedy approach consists basically of a finite iterative search that at each iteration recommends a new set of road paths. As expected, the roads are based on a weighted Dijkstra with linked weights based on the relative number of overlaps from the input graph, but which continuously change at each iteration. At this step, the overall number of overlaps is checked at each iteration, eventually until it gets 0, or until the maximum given number of iterations is reached. Finally, the output of the method is what is deemed the optimal set of road paths, which is the set of paths which provides the minimal overall number of overlaps, so the best solution. And note that as different from the literature, here we provide a set of roads for a network which in overall has a lower overlapping degree, thus with the aim to improve the overall network schedulability. Other approaches generate routes one by one until each of the flows becomes schedulable, thus having a per flow approach. We assess the performance of our proposed method by simulations. We considered 100 random test cases for both the flow and topology generation, and we compared the performance of our approach against the classical shortest path method. The red lines in the figures show the results obtained with our approach after 100 iterations when compared to the baseline in blue. As shown in the figures, we observe that our method provides significant improvements in terms of the number of overlaps, while marginally influences the length of the routes. Indeed, the amount of overlaps is reduced by a factor of half or more, depending on the network load conditions evaluated. Note that in the figure, lambda represents the median vertex degree of the network, a factor related to the network density and connectivity degree. On this respect, we observe that by increasing this factor, for example, from lambda 4 to lambda 12, this is having as median 4 or 12 neighbors for direct connection of each node, an improvement in terms of both the average road length and the average number of overlaps is observed. This despite the overlapping degree of the road paths, but that can be further improved by the impact of our method. In consequence, we observe that the effects on average worst case transmission conflict demands associated with the reduction of overlaps is also significant, again, by up to 50% or more, while having a marginal impact on the channel contention. Again, a similar effect derived from the connectivity degree is observed on both contention and conflict demands. More importantly, in terms of schedulability, the results obtained are promising, achieving up to 50% and more of better schedulability ratio under varying network configurations. These results are consistent with the significant reduction in terms of the overall number of overlaps in the network. In addition, we also observe that although in general, increasing the number of channels might provide better schedulability results, on the network configurations evaluated, this effect was negligible at a given point, therefore showing a dominance of the transmission conflicts over the channel contention. In any case, under and equivalent availability of channel resources, our approach performs better, allowing to allocate, in general, considerable more network flows. As discussed before, when analyzing the results at varying network connectivity, we observed that this factor results to be decisive, also for the scalability. In fact, as shown in the figure, at certain network conditions, more than the double of the network flows might be allocated if a high degree of connectivity is combined with our minimal overlapping routing approach. All in all, we have developed an effective real-time wireless routing framework for TSCH-based networks under EDF. The concept of our method is simple, only based on a grid heuristic for path overlap minimization, which is able to successfully reduce transmission conflicts while improving schedulability, notably with marginal impact on contention and road path length. We conclude saying that we consider the prospect of this method promising, both as a general technique to reduce conflict delay or as a novel framework for joint EDF scheduling and routing that provides better real-time performance in TSCH-based networks. Thanks for your attention.
Okay. As usual, can you still hear me? I think so, but
yes,
better
thank
check.
you.
Okay. Let's see if we have question. I will repeat it again, and I will do it after every paper just to make sure that someone hasn't entered later. That this workshop is being recorded and will be uploaded on YouTube as part of the HiPIC policies. So you can ask questions either via the chat or using your voice. If you don't want your voice to be recorded for privacy reasons, just use the chat. Let's have a look and see if we have questions. Okay, we still don't have a question. In the meantime, as usual, I will ask a question myself. As you probably know, I am developing basically networking stack for real-time embedded systems for in particular mesh networks. It's called TDMH, and my question is, you applied this optimization in particular to TSCH networks, to time-lapse channel hopping. But how easy it will be to port it to other networks, such as, for example, our TDMH? I mean, how general it is?
If I remember well, it could be applicable to that one, because this framework is for multi-channel TDMA. So because it's basically based on the schedulability analysis. So schedulability analysis provide the performance in terms of worst case. So this is not, I would say, like best effort performance. So it's the worst case. So it's a real time. And since you have if you have a mesh network with multi-channel, it is applicable. But maybe you don't have EDF. If you don't have EDF, the schedulability analysis will change. But the routing approach combined with a different scheduler could also apply. So from the point of view of worst case analysis, it should provide better results.
Okay. Maybe we can discuss it maybe later, because we need to go on with this.
Yes.
Work. Okay. Sure. Thank you for answering the question. Okay, I see that there are no questions from the attendees, so I think that we can do the first break. It will be a 10 minutes break that is suggested to help keep people focused. Okay, so I say that I will pause the recording and we will see in about 10 minutes. Okay. Okay, now I have resumed the recording. That's fine. So the next paper that is going to be presented here at NGS is event-based control enters the real-time world, perspectives and pitfalls. The presenter is Silvano Seva, which is from Politecnico di Milano. You can present yourself and then start the presentation.
Okay. Good afternoon. I'm Silvano Seva from Politecnico di Milano. I'm a second-year PhD student. My research area is systems and control, and this paper belongs to one of our research lines, which is about event-based control techniques, which means that we are developing control systems made such that the control action is not always applied to a system, and this can lead to advantages because when the system is steady state, you do not have to continuously apply a control system, control action on the process. And the last year we have presented a sensor node for event-based control, and this year we are presenting this research paper in which we have started to analyze the effects that an event-based control system has on the real-time performance of our overall system. Okay. The context is the one of the so-called wireless factory, which is a term which basically describes something which is happening in the last years, which is a wide usage of wireless devices in the industrial world for monitoring and also for process control. Using wireless devices for control and monitoring implies basically two major challenges. One of them is that we have now tighter energy requirements because these devices are naturally battery powered. Otherwise, we lose all the advantages we have of going wireless. And also, we have strict demands in terms of bandwidth occupation because the bandwidth allocated for wireless communications is a bit strict in some sense. So we have a lot of devices trying to exchange data in contain a small shared resource. So this can be a challenge. However, we have that event-based control techniques can help in mitigating these issues because their peculiarity is, as I said before, exchanging data only when needed. That is, we need for measurements of the process output, and we have to send control actions only when we have to apply some change to the process. For example, to bring back the controlled variable to its steady state, to its set point. If I don't have to perform any action on the controlled plant, I do not need to exchange data. And it is apparent that in this way, we can save both energy and bandwidth, because if we don't have to act on the plant, we do not send anything. However, from the real-time point of view, event-based control poses at least two major challenges. One of them is related to control latency, and the other one to task scheduling when we have multiple controllers running on the same computing architecture. And I will describe these challenges in the due course. Before analyzing them, I just want to give a brief description on how event-based control works. Here we have an example of how the events are generated. We have an example of one output variable of a process. The so-called band is a dead band, and we have that as long as the process output lies inside the dead band, no data is sent to the controller. because we consider this deadband as a safe range for the process variable. Whenever the controlled variable goes or either below or above the deadband, we have that the sensor, which is continuously sampling this variable but not sending data, starts transmitting a burst of data to the controller to allow for a control action. This is better shown here. We have in red the controlled variable. In dashed green, it's a set point. Here in blue, we have the control signal. And here below, we have the temporal distribution of the transmissions. In this case, we have events in correspondence of the set point changes, but we can have events also for disturbances. How the events are generated in this case is not really important. But the important fact is that here we can see that data, here each bar is a transmission burst. We have transmission bursts only in presence of changes to be done to the controlled variable. In this case, for change of set point, we change the set point here, so we have to send data to apply a control action. Here, we do not have to do anything to the control variable, so we do not send data. These transmissions here are basically due to presence of a timeout period, which is just to avoid running the system in open loop for too much time. Okay, as regards the control latency, we can define it as the amount of time passed since some fact occurs, a set point change, a load disturbance, something like this, till the controller reacts with a control action on the plant. And we have that with fixed rate control systems, this control latency is always bounded, because having this system continuously sampling and applying a new control action on the plant for each time step, we have that the reaction to any change happens in a time which is at most equal to one control period. However, with ABC, which stands for event-based control, the above statement is not valid anymore. This is because the control latency is influenced by different factors, which are the event triggering mechanism, the presence of a timeout mechanism, the width of the delta, and so on. This because we have, for example, we have something which perturbs our process output, but unless the motion of the process output goes below the delta or we have a timeout, we do not have any control action on it. So we have this latency, we have a wide variability of this latency, for example. And to better analyze this latency, we have forged the idea of cyber-physical control latency, which is a concept which better describes the latency by dividing it in two parts. The first one is the cyber latency, which is the latency which comes from the network and computer infrastructures. Basically, the round trip time is a contribution to the cyber latency. And the physical latency, which comes from the process structure and its interactions with the outside world. And as I said before, in the fixed rate case, the control latency is mainly cyber, because any perturbation is detected within at most one control step. The low physical latency is slow and bounded and equal to at most one control step. And all the overall control latency is composed for its most by the cyber component, which is a good situation because this cyber latency can be estimated or measured and conveniently compensated by ad hoc techniques which are available in the literature of the control systems. With EBC systems, we have that the physical latency is greater than the cyber one, and it has a huge temporal variability, and this it poses serious challenges. And we have identified two major sources for this high variability of the physical latency. One is due to the delta of the threshold. We have that, for example, here in blue, we have that something caused this perturbed motion of the process output, and we can see that an event is generated here or here or here, but the time passed since we have the event and the effective transmission depends on how is fast the rate of variation of the process output. Another case is that we have, for example, a variability induced by the presence of a timeout mechanism. We can have, for example, a disturbance which causes a perturbation of the process output, but the motion of this perturbation still lies inside the delta, and we do not have a detection of this perturbation until a timeout happens, which forces a transmission of data and the computation of a new control action. So we have these two major sources for the variability of the physical latency with event-based control. Coming to task schedulability, we have that event-based control tasks are sporadic tasks, but they still have strict requirements in terms of periodic execution. I mean, they have, in presence of transmission, because we have an event, we need to compute control action, we have to run the controller at its time step for a given number of steps, but we must respect the time step at which the controller has to be run. Otherwise, we have bad results. So we have sporadic tasks with strict requirements in terms of periodic execution. And we have that their time distribution in terms of life of the process is strongly influenced by outside phenomena. So their contribution to the overall CPU load is not constant, because even as long as we do not have to act on the process, these tasks are basically in sleep state, so they do not need for the CPU time. When we have to compute and apply a control action, of course, they become ready, they need for CPU time to be executed. And we have identified that there is the possibility of what we have called as event storms, which are events in which we have a large number of ABC tasks woken up in the same time. We are under the hypothesis that we have one computing infrastructure, for example, one CPU running more than one event-based controller, which is not a rare situation. I mean, it's quite common. So in case of EBC, in case of event storms, we have a large number of these tasks woken up at the same time, requiring each one for its CPU time. And this can lead to a CPU utilization factor greater than 100% if it sums up with the other tasks which are already present on the system. The other challenge we have found regards network synchronization, and this because in wireless control networks we have that TDMA, which stands for time division multiple access scheme, is a widely used technique just to allow each device to transmit to its master node without having to perform access contention mechanisms, just to have the safety that data is transmitted without the need of acknowledge mechanisms and so on. But we have that a wide variety of these protocols base their synchronization on the fixed rate behavior of the transmissions, which comes with fixed rate control. With fixed rate control, I have the sensor which transmits data to its master node at a fixed and known period, and protocols like wireless HART use this characteristic to keep all the network nodes synchronized. With ABC, we do not have anymore that a wireless node transmits data to its master with a fixed rate. It transmits data only when needed, and so we do not have anymore a reference signal for synchronization, as I described here. Then another challenge, which is brought in by EBC when dealing with network synchronization, is that EBC needs for each time slot in perspective. I mean, when we have that an ABC sensor needs to transmit data to the controller, we cannot afford to have packet loss. So we need to reserve a time slot for each possible transmission, even if this transmission does not happen frequently. And we have also tighter synchronization needs, because with fixed rate controllers, in some sense, we can afford to lose one packet, because we will have the next measurement in at most one control step. With EBC, this is not the case, because if we lost one packet containing one measurement, it can be that that packet is the last one of a transmission burst, and if we have lost it, we have lost it. Finish. There is no way to retrigger from the master a new transmission of data. So, coming to proposals we have explored for this. For what regards task scheduling, one possible approach, which is the conservative one, calls for considering all the ABC tasks as fixed rate ones with their time step, and to perform the schedulability analysis, and so to size the system in a way such that the overall task set, which contains the EBC ones, the other system periodic ones, the other fixed rate controllers, whatever, such that the overall task set does not reach the 100% CPU. In this way, we have that in case of event storms, in the hypothesis that we have an event storm triggering all the event-based control tasks at the same time, we are in a situation which at least we reach 99.9, for example, % of CPU utilization. We do not have a system overload, basically. And we can then employ slack reclamation techniques for reuse the empty ABC slots, time slots of CPU computation time, for example, for non-critical tasks, logging, monitoring, things like this. The other approach is quite different and calls for make a subdivision of the EBC tasks into different sets, because we can have, for example, some control loops which are tolerant in case of control degradation, because we can have systems where if we skip some control steps, this is not a huge concern. So we can subdivide the EBC tasks in these two sets. And then this way we can safely undersize, basing on the results we have from the previous subdivision, we can safely undersize the computing resources. And we know that we have safely undersized the resources. In case of CPU overload, for example, again, due to an event storm, we can skip, for example, some computation slots for the EBC tasks, which allow for performance degradation, to leave CPU time for all the other critical tasks in some sense. And as regards network synchronization, we want to achieve a more efficient bandwidth utilization, because we have said before that in ABC we need for how can I say, time slots for transmissions which will never happen prospectively. And so possible approaches are different, and are first one is employing again slack reclamation techniques for the reuse of the TDMA slots which are not being used by ABC. And if you have a strict synchronization system, you can assess if a slot is being used or not in reduced time. We can use carrier sense multiple access schemes instead of TDMA ones, but in this case we have the risk of collisions, so we need to manage this risk. And yeah, in case of collisions, we have effects on the cyber physical latency. I mean, a collision affects the cyber part of the cyber physical latency, and the cyber component is no more deterministic. It becomes probabilistic. So we have to size our system in terms of worst case cyber physical latency. And we have to do studies on what is the probability of having a determined value for the cyber latency. And however, control tasks are a bit more tolerant to latency and to jitter. For example, with respect to others, an example is if I have an FFT task, the jitter on data transmission can affect the results of the FFT. This is not the case for control tasks, however, so it can be sized that is not so detrimental. But we can also have hybrid approaches. We can have a transmission round where the first slots are strict TDMA ones and their latency guarantee, and to give guarantees in terms of latency. And then the other part of the transmission slot is accessed with a carrier sense multiple access scheme, and for all the tasks which are tolerant to data collisions, data loss, and consequent jitter. Okay, and in conclusion, we have that event-based control techniques bring into play significant advantages, especially with battery-powered devices, because reducing transmissions means reducing the usage of wireless physical devices, which are very energy hungry. However, we have these challenges when dealing with real-time systems and context. We have impacts on the CPU schedule, the feasibility of the CPU schedule. We can have the event storms breaking up our CPU schedule. We can reach over 100% CPU utilization. We have that the so-called outside world have a strong influence on the control latency through the delta and the timeout mechanisms we described before. And we started to outline some possible solutions for both the task scheduling and the management of the wireless communication medium. And future work will go deeper into their definition, and we will present some complete solutions to these problems. Thank you for watching and your attention. Okay. I cannot hear you. I don't know why, but anyway. The question is, in general, at which levels of the software hardware stack and how are these EBC techniques implemented? Are these methods in active use in current consumer grade PC laptops and IoT devices? Okay, to the first part, the EBC techniques are implemented at the highest level possible. I mean, at the application one. We have our for example, our sensor, which samples data and then forwards a request on the network. So they are talking about in terms of ISO OSI stack. We are at the application level. And are these methods in active use in current grade PC? To be honest, I don't know. But I think that the answer is no, actually. It's something which is beginning to being used. So I'm not aware of their use in consumer grade laptops or things like this.
Now you can hear me, I guess.
Yeah, okay.
Okay, yes. Sorry, but my microphone stopped working and I had to log out and log in again.
Okay.
In the meantime, I was able to switch the host to Silvano temporarily. If you can click on me and click make host again, like more and make host, then I can continue. Sorry, guys.
We want to change.
Okay.
Yeah. Okay.
Yeah,
Done.
that's perfect. Now I'm again the host and we can continue. Okay, so what I was asking, what I was trying to say before while my microphone was muted, is that I received a question to the presenters, which is, are all the presenters going to stay here till the end of the workshop? Because someone may want to ask a question even not immediately after the presentation, but later on. I would like to ask the presenters to confirm that you will be staying here till the end. I mean, Silvano already said yes, that's not a problem.
Yeah, I will.
Miguel is fine. Okay. Yeah. Philip is the last presenting, so it's not a problem for him. And so, okay, so it is possible to ask a question also not related to the immediate presentation, but also to the previous presentation. Okay, so that's fine. If you have other questions for Silvano, again, at the cost of being repetitive, I will have to say it all the time, that you can either use the chat or you can use your voice. But if you use your voice, you have to agree to the fact that this part of the presentation will be recorded, so your voice will appear in a YouTube video. This is not to demote the questions, okay? It's just for privacy reasons in general. Questions are, of course, very suggested. If you have questions, feel free to ask. I think there are no more questions for Silvano. So I think we can switch to the next presentation, which is M2OS MC, a real-time operating system for many core processor. The presenter will be David García Villaescusa, which is here. I think you're a PhD student.
Yes,
at the University of Cantabria, Spain, right?
Yes,
you can
right.
Present yourself and then start your presentation.
Okay. Hello, everyone. I'm here to present the new M2OS MC, which is an adaptation of an operating system to a many core processor. I am PhD student at the University of Cantabria, and I will reproduce the video I recorded for this Zoom session. So I hope you're ready, because here we go. I think we are on a schedule, so it's okay.
Yeah, we are ahead of schedule. That's not a problem.
Yeah. I'm really fast talker, so it will be a really fast presentation. Okay, let's go. Good afternoon, everyone.
Oh, no, now we can. Now we can. That's fine. That's fine.
Ah, yes.
Go on. Yeah.
Okay.
Sorry, it took some time.
Ah, okay.
Okay. My name is David García Villaescusa, and I'm here to introduce you to the real-time operating system for many core processors called M2OS MC. I work it alongside Aldea, Rivas, and Michael González, Harbour. We are all working at the University of Cantabria. I'm going to talk to you about many core processors and some motivation here. The main motivation is that the number of logical cores is increasing exponentially, while the single thread performance and frequency are stalled. So, processors are tending to have more and more cores in the same chip, and they are connecting themselves and connecting them to external devices in several ways. The multicore processors are currently widely used. They are used everywhere nowadays, and even in the smaller embedded system. The multicore processors are really hard to use in real-time system because they are constrained to achieve the required predictability. This is due to the shared bus which connect the cores with the shared memory and, well, the cores between them. This is really low scalability, and this is really bad for us. But many core processors have solved this bottleneck, mainly using the 2D mesh network on chip, which can be seen here, and that gives us a predictable delay on the communication between two cores, and the power consumption is linear with the number of cores. We are using the Epiphany processor for this project. This processor has a 4x4 mesh network chip. In each tile we have an E-core, which is executing the frequency of 600 MHz, which is the same frequency of the network chip. Each tile will have also local memory, 32 kilobytes of local memory. And we are using the Epiphany processor in a parallel board, which is kind of represented here, which have a sync, which is an ARM based processor, and we also have some shared memory we will avoid using because this timing is really bad in comparison with the local memory of each tile. In each tile, we have the XY NOC routine performance by this router. Okay, this router over here will perform an XY routine with a round-robin arbitration. this router is able to dispatch one packet per cycle and link. And I would like to notice you that these links are bidirectional links, okay? Apart from that, it will be good to know that if we have here a packet in this link going to the east side of the router, it will take 1.5 cycles to reach this other link. This if we don't have any other traffic, okay? Well, so just I want to let you know that this eCore could write or read, could write to and read from the local memory of any other eCore in the NOC, and this will be transformed in NOC messages. I'm going to talk about the operating system itself. It is based on M2OS, which is a small and fast real-time operating system kernel that allows multitasking application. The tasks here are non-preemptive one-shot, which means that you have the same stack area for all the tasks, and this is really good for context switch timing. The operating system is written in ADA, and for the many core implementation, we have several instances of the operating system replicated in each tile. In this case, as we are talking about the Epiphany, we have 16. We have the hardware dependent part encapsulated in the hardware abstraction layer, and I'm going to talk about this right now. We have developed several stuff here. The context switch, which is really fast, as I said before, only requires resetting the stack pointer to the base position and setting the program counter to wherever you want to go. The interrupts, fully functional, the core identification to know where at what core are you executing at. The spin lock, which is an unblocking, multi-array execution, synchronization, the system timer that just updates the system clock, which is 32-bit integer with 1 millisecond resolution, and the high precision lock with less than 2 nanosecond resolution, and is suitable for intervals up to 1 millisecond. As the sync doesn't start the Epiphany cores at the same time, but one by one, each core has independent timers, and the timers begins when the hosting eCore starts its execution. The timers of the different cores will have a gap between them. To solve this, the eCores with our OS wait for a message from the last eCore started. This message contains the timer value adapted to delays of the messaging system. The console. In this parallel board, the system console is managed by the sync processor, and none of the eCores of the Epiphany has access to the console. So we have implemented a console service for the eCores. These eCores write into the reserved memory of the local memory area what they want to show at the console. So the sync processor could just read the console reserved memory access of the local memory of each eCore and prints its content. Now I'm going to introduce you to some performance metrics done to the operating system. The first one I want to introduce you is the clock read and the mutex operation. As it can be seen, we have the same values as max, minimum, and average values. So this is pretty constant timing. For the context switch, as I told you before, the context switch is really fast for the simplicity of the OS. So everything is done in less than 1 microsecond, and it's pretty constant also. And lastly, I would like to talk to you about the size of the eCore instances. As it can be seen here, it doesn't really increase a lot with the number of tasks. We have 2 and 6 tasks, and well, it's bigger, but not much bigger. Now I'm going to talk to you about the intertask messages we developed for this OS. And as real-time typical application is formed by end-to-end flows, which are formed by several amount of tasks, one communicating with each other, and those tasks could be mapped at different eCores. So we would like to communicate them in a synchronized manner. So we got inspired by the RTOS sampling port, and we have one message per sampling port, while we have several sampling ports that could be at one e-core, right? We suggest you to use periodic pooling with the sampling port just to avoid blocking the e-core. And so now the typical consumer and producer example, the consumer, as it can be here, is the one who has the sampling port. This is due to the fact that writing is faster than reading, so the consumer is having the sampling port and the data where we want to store the messages. We are here having two loops. One of them is just reading the sampling port again and again and again until it get a new messages. When it get a new message, the loop will end and we could work with the data. And again, we will do it again because this is a consumer, just consuming data. For the producer, we have again two loops, but this time they are not one inside each other. It's consecutive loops. So we get the sampling port here, and until we get a good sampling port, so until the consumer has initialized its sampling port, we will be waiting here, getting the sampling port and waiting for the consumer to initialize it. And then we can generate data and write all the data we want to, independently of the consumer consuming actually our data. We could write it again and again without needing to check anything. And we made some tests about that, about these inter-task messages, and I'm showing them now. Okay, here we have init sampling port and the read sampling port done in the same e-core, and the get and the write sampling port done in a different e-core with a distance of just one router. Okay, it also can be seen that it's pretty constant, the timing, really constant, except for one exception, but it's slightly worse, but I think it's not strongly worse, so we are happy with this. And another thing I want to tell you is that this is synchronized messaging, that we have a spin log to take and everything. For the e-core itself, everything is measured in the e-core performing the operation. It gets worse, the timing. Well, it gets longer time to perform the operation due to the distance between e-cores. This is just because we have to travel to the other e-core, get the spin log, got back with the spin log, and then sending the message. So this process increased with the distance, and it's worth for reading. The increase is bigger than for writing. But as it can be seen now, here we have round trip latency. So we have a message, for instance, in the 0 tile, and we are going to send it to the 3 tile, and we have to get back the message again. So this is even worse, taking into account the distance. But if you compare it with the size of the message, it doesn't get much worse. It gets slightly worse, but it's not a big increase. Okay. I'm going to talk to you now about the conclusions and future work. And as conclusions, we can say that we have successfully ported the M2OS to the Epiphany many core, and the synchronization mechanism implemented is, well, obviously inspired by RTOS, the sampling port done by them, and we support end-to-end flow applications. We think that our performance tests show an acceptable low latency. And as future work, well, we will love to develop the RTOS queuing ports, and we will like to develop a system model that allows us to perform stability analysis of the application using M2OS. Actually, I'm working on it right now. We would like to also develop task allocation algorithms just to optimize the end-to-end flow of response time. and it will be great to extend the application model by allowing some cores to execute OpenMP workloads. Okay, so this is my presentation of M2OS MC, and I will like you to ask me any question you have. See you.
Okay. Okay, I guess that you can still hear me this time.
Yes,
Okay.
this time.
That's perfect. And I see that some new attendees have joined, so I would like to remind them that the program for this workshop is already online. I wrote in the chat the link to the program so that you can go there and you can find not just the program but the proceedings, so that you can download all of the papers right now if you are curious and want to know more. The other thing is that, as usual, you can ask questions, also not related to this presentation, also related to the previous presentations. You can do so using the chat or by voice. If you do it by voice, however, keep in mind that your voice will be recorded and uploaded to YouTube together with the entire presentation. We have some questions. I think that David can already see them in the question and answers, and so he can reply directly.
Okay, yeah, I can see them, both from Tony Pustinen. I hope I say rightly the name. So the first question is, what will be the use cases for M2OS? For example, in what kind of situations could other researchers be interested in working with it? And how does it compare to other small OSs? Okay, actually, we are using it for checking our models in many core systems. We have a modeling tool which is called MAST. You can find it in mast.unican.s. And we are analyzing the different systems related to applications for many core processors. And we are now doing a little bit dummy things, like quite simple stuff right now. And we are kind of guessing what we can be achieved with that. But the results that we are getting with the real operating system execution, the different tasks and the different end-to-end flows, we are using that to compare our modeling, our model with for many core processors, because we are modeling actually 2D mesh with that, which is the same thing about the same thing as it is done with the Epiphany processor. So at least for us, I don't know for others, I hope it will be useful for somebody else. But for us, it's useful to compare our models with a real processor working and actually executing synchronized messages. Okay, for the next question.
The question is asked, so is answered. So we have another question.
Okay. Okay, this question is from Kovatsasi Tamas. Again, I'm sorry if I mispronounce it. One addition, your clock resolution is... I have another precision. You will see. Okay, well, that's actually an addition, not a question. Okay, he's saying to me that my clock resolution is 1.9 nanosecond. So I don't know its precision. To know the precision, I should need some measurements which compare my clocks with the reference clocks. And yeah, that's true. I should use that word. I was messing with my English there, but yeah, that's true. Yeah, I should use the word resolution, no precision. Yeah, sure. And if there is any other question there.
Yes, okay, I think this question is answered. I think that someone else may be typing. Yeah.
Yeah, I got the number, but
yeah, if you go to the answered question, I probably accidentally marked as answered the second question by Tony Pustinen. That is a different one. I just thought it was the same repeated twice. Sorry. So if you go to the answered, you have another.
okay, yeah.
Yeah.
No real. Okay, yeah. It's Tony Pustinen asking me. In this context, you are talking about real-time OSs, but what about not real-time OSs? What will be the use cases and concrete examples of non-RTOS? Actually, you can use the Epiphany processor in quite a simple way, just using the tool they gave you, and it delivers a reasonably okay power consumption per potency there, or per computing capabilities per flop. Maybe it will be the next comparison there. So it is quite good, for instance, for Bitcoin mining. It was widely used for that purposes, actually, which is kind of funny because well, now it's not used for that anymore. Actually, there are better things to mine with, but it got a really small, like really small power consumption, like 5 watts or something like that. I don't remember the number, but it was like for the watt, it has really nice flops. So anything you can do with an embedded system that requires a little computation power and trying to get a more, even less consumption, it will be great for that. Something like working with batteries or something like that, it's a good choice.
I agree. I also have a very fast question, which is, you mentioned that your operating system is non-preemptive. Is it a limitation of the Epiphany or a design choice?
It's a design choice. It's the same limitation that we have on the Arduino implementation, for instance. So we choose that because the context switches are really fast. You can reuse the stack space. You only need to
okay, I see.
Yeah, to set the stack pointer again back, and well, and the program counter, of course. Yes.
Okay. So I think that if there are no more questions, we can have the second break. We are more or less 30 minutes ahead of schedule, but it was anticipated that the schedule was compressible. This is true for basically all of the HiPiC workshop this time, because they decided to not have like common coffee breaks, so the schedules can compress and expand as needed. So I think that we will see us in about 10 minutes for the final presentation.
Okay, thank you. Bye.
Thank you. Here we are again for the final part of the NGVS workshop. The last presentation is static allocation of basic blocks based on runtime and memory requirements in embedded real-time system with hierarchical memory layout. The presenter will be Philip Jungglas, but he has decided to not be recorded, so I will pause the recording and we will start with the presentation. Okay, the final presentation has been done. Thank you everyone for attending the next generation real-time embedded systems workshop. It was unfortunate that this year we had to do it online instead of in person, but of course these are difficult times. And thank you very much for attending again, to all of the attendees and to all of the presenters. And we hope to see you again the next year at the next NGVS workshop, hopefully in presence.